Welcome to the Chapter 14 Problems kind of guide. It says Chapter 14 Review. This is really just the way we do problems. I've always worked with this formula or these worksheets to kind of give you some practice with Chapter 14. There are a few things here that you have to be careful about, but let's kind of walk through a number of these problems. Some of these are quite easy. Some of them are a little difficult. Number one is asking about finding 5 randomly selected graduates, all within their chosen field after graduating, finding a job. And we know that the probability of finding a job after you graduate is 0.75, right? We know that I want to, when I'm working on a problem like this, I have to decide between the and or the or scenario. In this case, it's asking for 5 people to find a job at the same time. That's an and question. It would be you and you and you and you, all 5 people all together finding a job. That would mean if they're independent, I can multiply them together. In this example, we can find out that they really are separate and independent, because if one person gets a job in a totally different field, in a totally different part of the country, it isn't really going to have an impact in me finding a job in my field. So we can make a reasonable assumption that it is independent. So we can multiply 0.75 together 5 different times, or I can simply take it to the 5th power. It would be D 0.2373. In number 2, we are looking, it says in the question, it says, what is the probability that neither of your 2 groups, group mates, has studied statistics? So neither is kind of implying that neither one of them at the same time. So neither is a negative version of and, right? It says, what's the probability that neither of them has studied statistics at all? In this example, we know that not studying any statistics have never taken a stat class would be 0.25. So it is very similar to number 1. 0.25 squared is 0.0625. If I round that to 3 places, we end up getting answer choice E. So 1 and 2 definitely tended to be very similar in their problem type. It was an and question, and they were independent. In number 3, it says today is March 9th. There's 108 people in the room. What's the probability that at least one of them has a birthday today? I don't know if you gathered this through the reading, but in Chapter 14, there is a really important concept called the complement of a probability, right? So at this point, let me kind of make sure that we all know this. At least one is a phrase that I look for. And when I do that, I can do this formula. 1 minus the probability of none. It's equal to the probability of at least 1. Okay, let me put this up here. Probability of at least 1 is equal to probability of 1 minus the probability of none happening. If you really attempted to do number 3 straight through, this is an incredibly long problem. Probably longer than it would take you for an entire class period to work out. It would mean that there's 109 problems that I have to complete, and neither one of those are very simple. Just for example, if we wrote out a distribution table, a probability distribution table, then it would look something like this, right? We would have, well, no one could have a birthday today. 1 person could have a birthday today, or 2, or all the way up to that 108th person could have a birthday today, and everywhere in between. That's a lot of things to work out. Just the probability of finding the probability of getting all 108 people. Well, what's the probability that 1 person has a birthday? If I had every day of the year, let's assume it's just a traditional year, and I reached in and grabbed a date, what's the probability that I could select your birthday? Well, that would be 1 out of 365 times, right? I want to be able to do that for all 108 people, right? If I picked March 9th, what's the chance they all had a birthday today? Well, this would be 1 out of 365 to the 108th power. That's a pretty tiny number. And I'm going to do that for every single value. And let's be really clear. Finding the probability of 108 people, that's everyone having the same result. That's very different than finding the person, let's say, that has 1 birthday. That would mean I would have to do that 108 different ways, and I would have to find that probability and then work that out. And then I have to do it for 2, and then for 3, and all of this makes something that's just way difficult. So there's a much easier way. We know that when you have a the sample space, which this is every possible outcome. If I were to add up all these values right here, that is the thing I don't want. Or that would be, that's the actual answer I want. I want to add them all up. The one I don't want is this one. I don't want to find that one. It says at least one. That would imply one or more, right? 1 up to 108. So if I can find this, what we know is the probability that the sample space occurs, that something from the sample space is equal to 1. With that knowledge, that means that I can say 1 minus the probability of 0, and that would equal at least 1, right? That's the phrase we were looking at earlier. So we need to figure out what's the probability that no one has a birthday today. So if I do that, we know that the probability that 0 people have a birthday today would be, well, what's the chance that I reached in for one person and grabbed not your birthday? Well, there are 364 days out of the year, out of 365 days, that are not your birthday, right? Well, I don't want to do that for just one person. I want to do it for all of them, right? I'm going to do that to the 108th power, and that's going to give us 0.75 something. And that's the value that tells me that's not your birthday, right? That's 0.7436. 0.7436. That's the probability that 0 people have a birthday today. I wanted to know at least 1, so we're going to do 1 minus 0.7436, which is equal to 0.256, which turns out to be answer choice C. That's pretty deep in terms of a problem. But the illustrated point was I wanted you to know how to do this particular formula. I definitely would not ignore that. That is a really important aspect of this chapter. Let's move on. Number 4 is very similar to number 1, but it adds a bit of a complication. If I go down to the bottom, what is the probability of it failing to contact a household or contacting the household but not getting them to agree? So really, I've got a few things here. I've got an or clearly defined, and I've got a but. If we think about how that but works out, it's really saying I want to contact them and get them to not agree. So if I write this out, we want to find the probability of contacting the individual. Of failing to contact the household or contacting them and getting them to not agree, right? So not agree. And so this is an or with an and component. We always multiply before we add, so we're going to kind of work it out that way. If I look at the problem correctly, I know that the probability of failing to contact them is going to be 0.23. In this case, we have complementary events. I can either contact the individuals or not, right? So when I can't contact them, then the complement, so 1 minus 0.77 gives me the probability of failing to contact them. Or is the addition rule. And in contacting and not agreeing, well, we know that the contacting, there's 77% that are contacted. And then of those that are contacted, 32% will cooperate. That means that the complement of that, which would be 68%, would end up saying that they will not agree or not cooperate. So 0.68 would go here. And of course, we multiply before we add, and we can know that, once we work that out, you're going to get 0.754 as your final solution. Okay, so number 5, I'm not going to do this one because I want you to give a shot for that one. Number 5 and 6 are relatively straightforward as long as you paid attention to number 3 for number 5. This is the at least 1, right? So give that one a good shot. Number 6, totally the easiest one on the whole page. Without a doubt, it's really straightforward. Let's look at number 7. 7 at first looks like number 4, but if we go down to the bottom, what is the probability that the next household will be contacted but refuse to cooperate? Remember, I told you the but acts like and, so I want to do contact and refuse, right? So it's just a product here because we know that Being contacted or not contacted is very independent. They tell us that that's in the problem right here, independence. So we are allowed to multiply. Contacting is 0.77, but refused to cooperate would be 0.65, because that's the complement of 0.35. So here again, we are going to just be multiplying. That's going to give us 0.5005, which turns out to be D. Okay, number 8. I'm going to kind of talk about this. I'm not going to do this one because I think you can do this one on your own. Remember to think about what it's trying to find the probability. We want to find that no one is type AB. So I would like to know what's the probability that I am any other blood type, right? So they give you those, you can add them up. You want this to be true for 5 people. So make sure you kind of keep that in mind for these questions, right? So there's page 1. I didn't do them all. I think I want you to definitely, hopefully you've already spent some time looking at this, got some questions, and hopefully I answered those here. Let's look at a few others. Let's look at number 10. Number 10, you have a huge pile of buttons. 29% are black, 11% are blue, 17% are orange, 24% are white, and the rest are clear. It's going to ask me, the third button that I choose is the first one that's clear. That means I have 1, 2, 3 buttons. They tell us that you are putting it back in the pile. Why is that important? Because that means that every time I make a selection, the probabilities remain exactly the same. It's independence. That's what it's describing. That means that this one is going to be clear, and this one is simply, this is the symbol for not clear, and not clear, and then clear, right? Since they're all independent, I can multiply those together. We figured out, they gave us all the probabilities for being not clear. That's 81%. That would mean that the clear ones have a 19% chance of being selected because we added them all up. We know that the rest of them are clear, and so that allows me to kind of work that out pretty easily and get a 0.1246 as my answer choice, which is answer choice B, right? Don't let the wording here kind of confuse you when it says that the third one you choose is the first one that's clear. Just slow down, think about what it's saying, kind of go from here. Number 11, 12, 13, and 14 is really kind of talking about the definition of what it means to be disjointed or independent. A few tips. In number 11, they're talking about just a single event. You go to vote. So the idea of independence is not even on the table, right? If I don't have 2 things that are happening, then 2 events that are happening back to back, then I can't have independence. I can't even talk about independence. I think number 11 is pretty obvious that the answer choice is A, because we're talking about can you vote Democrat and Republican at the same time? Since that would be voting for a different candidate. You can't vote for 2 people at the same time, so that's impossible. Number 12, you are automatically talking about 2 different events. So now we do have independence on the table. It's about getting a 2 in the first roll and a 4 in the second. These events, because you are working with dice are automatically going to be independent, right? We have things, I can get a 2 in the first or second roll, I can get a 4 on the first or second roll. So it's not that it's disjoint, but we definitely do have an independent scenario. Number 13, I think, is probably the most logical. I am driving a car, we have 2 different events, right? Speeding and then getting a speeding ticket. So we do have the option of talking about independence. I would think that if you speed, right? If we speed, I am more likely to get a speeding ticket than if I were not speeding. So we definitely say that they're definitely not independent. We would say that they are definitely dependent. I can also get a ticket while I'm speeding. That tends to be how it works, right? So the fact that you say they're disjointed doesn't make any sense, because that would say that if you speed, you can't get a ticket at the same time, right? But that's crazy, right? So in this case, they are neither of those things. They are jointed and they are dependent. And number 14, again, is like number 11. It's 1 event, and you can't get a 3 and a 5 at the same time, so you have these kinds of things like that. 15 and 16, yet again, is trying to get you to talk about definitions. It's asking if in a random spinner can land on red, green, blue, or yellow. For the first 3 spins, it lands once each on yellow, red, green, or green, red, green, and yellow. Is it more likely to land on blue on the 4th spin? You would say no. it's a spinner. It doesn't have a memory. It would be independent. Each time you do this, the spinner would land on whatever, right? It says, so 15 would end up being A, no, because knowing one outcome will not affect the next. That's essentially the definition of independence. The multiplication rule says that probability of A and B is equal to probability of A times probability if they are independent, right? Not disjointed. Disjointed talks about whether the events can happen at the same time. Absolutely not. Disjointed and independence, these two things are exactly the same phrase. Mutually exclusive is just a lot to say at one time, so we tend to say disjointed. Okay? Next part, I want to talk about specifically 18 and 19. I'll let you do the rest of those together because they're a lot like what we've already done. To be legitimate, this is a probability distribution table. To be legitimate, you have to have where you add up all your probabilities. They have to equal 1. If they do not, they're not legitimate. If any of my probabilities are larger than 1 or less than 0, meaning negative, then they are not legitimate. If you add up either one of these two, they are not going to be legitimate because they do not add up to 1. It means I'm either missing an outcome or the probabilities are incorrect. So hopefully this short video really helps you to kind of make sense of some of these questions. 17, 18, 20, and 21 are a lot like the ones we've already been working on, so give those a shot, and hopefully you can get that done by the end of today. This is due tomorrow, or Tuesday night by midnight. Anyway, I hope this helps. If you got any questions, let me know.